For this lesson, we're going to be taking what we've learned about exponential and logarithmic equations, how they relate to each other, the different exponential and in particular laws of logarithms that we've learned, and that's going to allow us to start to solve equations where either exponential or logarithmic functions appear. If the unknown occurs in the exponent, which is what we have in this first case, there's a couple of strategies that we can make use of. One of them, and it's a typical strategy, is actually really useful in mathematics and physics, engineering, is you take the logarithm of both sides. So we're going to do that second. We're going to start this just by using the approach that we've typically used, which was we've made use of the definition of the relationship between an exponential function and the equivalent way of writing that in terms of a logarithmic function. So we're going to take a and we're going to write it that way. So in this case, it's in the form y equals a to the x. So my x, my exponent here, is actually this more complicated x plus 2. And that's equal to log base of 3, and 4 becomes the argument of my logarithmic function. Now this is log base 3 of 4. Well, let's isolate x. Log base 3 of 4 minus 2. And just make sure it's really clear in your mind that this is log base 3 of 4 as a single unit and then subtract 2. The 4 minus 2 do not go together. But for many people, and from a skill point of view, so for many people, first of all, not everyone has a calculator that will calculate log base 3 of 4. But even if you do have a calculator that can do that, you need to know how to break this into a log of another base. Now typically we do base 10. And the way we do that is we write a fraction. So we take log base 10 of 4 over log base 10 of the base of the original logarithm, which was 3, minus 2. And we're now at the point where we should be able to come up with a numeric value for this. So I'm going to take the log of 4, divide that by the log of 3, and I end up with 1.2618, and I'm going to subtract 2 from that, and I end up with negative 0.73814. Because I say here, check your solution. And so the way I'm actually going to check my solution is I'm going to say, okay, my left side is equal to 3 to the x plus 2. And that's why I kept so many decimal places here, because now I'm going to take that value, and the best way to do this is to actually keep that value in your calculator, as I have done. I'm going to add 2 to it. So I ended up with 3 to the power 1.26186. 1.26186. Lots of decimal places there. But again, I'm keeping these in my calculator, so now I can just say I want 3 to the power of my previous answer, and it turns out that that is equal to 4. So I know of course, my right side was just equal to 4, so my left side equals my right side. Okay, so having done that, now I'm going to take the log of both sides and show you another way to do this same thing. Now I think to do this one, I'm actually going to start by rewriting the problem. 3 to the x plus 2 is equal to 4, and I'm trying to solve that. So what I will do is I'm going to take the log of 3 to the x plus 2 equals the log of 4. And now that I've taken the logarithm, I can actually make use of one of our laws of logs, which is something we talked about in a previous lesson, which is if I have the logarithm of x to the r, that's the same as r logarithm x. So this r comes down in front and becomes a multiplier. So the same thing is going to happen here, which is this exponent is going to come down in front as a multiplier. And what's left behind is simply the log of 3. Notice I'm not saying log base 10 this time. You need to get used to the idea that when it just says log, that is log base 10. And that's equal to the log base 10 of 4. Now I want to isolate x, so the first thing I need to do is I'm going to divide both sides by log of 3. And I end up with x plus 2 is equal to the log of 4 over the log of 3, which means that x is equal to the log of 4 over the log of 3, subtract 2. And that is exactly what we ended up with in the previous method of finding the solution. All right, now for solving this one, there are a couple of ways to solve this one, and both are equally valid. It just depends on which way you see it. Now, generally, I think in terms of isolation. So my first instinct is going to be to get x all by itself. Log base 2 of x equals log base 2 of 6 plus log base 2 of 3. Now in this case our logarithms are base 2, so we do have to keep things separate. Just a warning here, most people, you recognize you're trying to use laws of logarithms, but some people are going to look at this and say, well, doesn't that mean that x is equal to 6 plus 3 because I've got addition? But that's not the case. We have a specific law of logarithms to help us deal with this, where we have the sum of two logarithms. That is actually the same as the product of the arguments or the inputs to those logarithms. So that's going to be log base 2 of 6 times 3. So then we end up with log base 2 of x is equal to log base 2 of 18. And just as we did before with exponentials, you take a look at this and you can say, well, since this is log base 2, this is log base 2, this x must be the same as this 18. But if you're not satisfied with that, you can actually we can go one step further, which is we can take 2 to the power. So we can take each side and we can put it into the exponential function 2 to the x. So 2 to this whole thing must be equal to 2 to the, and I just want to show you this is an alternate way of saying this, because here we have the exponential function 2 to the power. Here we have the logarithmic function base 2. We know those undo each other, so all that's left from that is x. And here we have 2 to the log base 2, which that essentially nullifies or undoes each other, and all we have left is 18. Now, you could also have gone straight from here to here. Normally, if you're going to go straight from here to here, you say something like this double arrow, which says this implies, the fact that these two look the same implies that this x must be the same as this 18. Whereas if you follow it through here, well, you could argue that it implies this one as well. Now, another way we could have done that is we could have taken care of these two terms right away and left the right side alone. So, or, let's go down here. Or another way I could have done this is I could have combined this subtraction or difference of logarithms, which forms a quotient. So that becomes log base 2 of x divided by 3. A difference of logs is the same as the log of a quotient, is equal to log base 2 of 6. And that means these are the same, so that means x over 3 must be equal to 6. X must be equal to 18. And you can see we got the same answer in both locations. All right, solving this one. A couple of ways to do this one, but really I think that the way that makes the most sense here is to take the logarithm of both sides. So I'm going to say the logarithm of 6 to the 3x. You could do with the brackets or without the brackets. I often put in the brackets just to make really clear what's inside the logarithm and what's not in the logarithm. And that's more important when things are complex. We have the rule that allows us to take an exponent of a logarithm and move it in front. You don't have to draw this arrow when you're doing your own work. I'm just trying to make that clear. So that's 3x multiplied by the log of 6. Notice I'm dropping the bracket here. Log of 6 is pretty clear. And this becomes 2x minus 3, all in brackets because that whole exponent is now a multiplier of log of 4. Now, at this point, there's not much more I can do because I need to get all of my x's together. And the only way for me to get my x's together is to expand out this term on the right side. So I actually have to leave this as 3x log of 6. And this one becomes 2x log of 4 minus 3 log of 4. And as we would typically do, we're now going to group terms. So we're going to gather together all of our x's on the left side. 3x log of 6 minus 2x log of 4 is equal to negative 3 log of 4. Now I've got a common factor here of x. So I divide out the x or factor out the x, and I end up with 3 log 6 minus 2 log 4 equals negative 3 log 4. So this x all by itself is negative 3 log 4 over this entire thing. 3 log 6 minus 2 log 4. And from there we end up with approximately, and I go to the calculator for this one. Now be really careful when you do your calculation here. If your calculator has brackets, then make use of it. If your calculator doesn't have brackets, do each of these calculations separately and store them to, or write them down to, a significant number of digits. I would say probably maybe 5 or 6 decimal places. Minimum 4, 6 is safer, and then come back to do your calculation. I'm going to do this whole thing in one shot on my calculator. So negative 3 log of 4, and I've done that in a set of brackets for the numerator, divided by, so just to remind you when you're doing this, your numerator and denominator should get, if you're doing this on your calculator, it's always a good idea to do separate sets of brackets for those. And then inside my denominator bracket, I have 3 log 6 minus 2 log 4, close bracket, equals, and I ended up with x is equal to negative 1.5979. Now, if I'm writing my final answer for x, I might write that, depending on what's specified, I might just write that as negative 1.6. But I want to keep these extras here because I'm going to just, it didn't say to do so, but I'm going to go ahead and do a left side, right side check on this. So my left side is equal to 6 to the 3x. So that's equal to 6 to the 3 times negative 1.5979, at least approximately equal to that. And that works out to be 6 to the power 3 times negative 1.5979. Now this time I'm not keeping all of my digits in my calculator, so I end up with 0.000186. Now by not keeping all of my digits, by just using this rounded to 4 decimal place answer, I want you to see that it should be close, but it does have an impact. 4 to the 2x minus 3. I'm just going to go ahead and do that one on my calculator. So that's 4 to the power, bracket, 2 times negative 1.5979 minus 3, close bracket, equals, and I got 0.000186. So I didn't lose any precision, at least enough so I can convince myself that left side is equal to right side. So keeping those decimals, if I had done this same thing with negative 1.6, I think you would have seen the left side and right side would have been close, but they wouldn't have been this close. Okay, solve log of 0.04 equals negative 2. When I look at this, the obvious way to do this to me is to make use of the laws of logarithm, or not the laws, the basic property, the definition, which is y equals a to the x is the same as x equals log base a of y. So in this case, I've got a logarithm, log base a of y. So my y value is here, 0.04, equals my a value is x, so that's x to the negative 2. So a couple of ways we can approach this. 0.04 is equal to 1 over x squared. And then I'm going to cross multiply. I get x squared equals 1 over 0.04. X squared is equal to 1 over 0.04 is actually 25. X equals plus or minus 5 if I take the square root of both sides. But what is x? X is the base of a log function. And that tells us that x must be greater than 0. X has to be positive. So we end up with our answer here is just x is equal to 5. If you were to try to take negative 5 and take the log base negative 5 of 0.04, you would end up getting an error. It wouldn't know how to calculate that. And if you remember our graph of logarithms, it looks like that. You can't even put your x value, you can't even put in an x value of negative 5. It's only defined here for positive x values. And solving this one, I've got x's in two separate logarithmic terms. So I'm going to combine these. I've got a sum of logarithms, which is the same as the product So I've got this product. A logarithm of the product is the same as the sum of the logarithms. And the way to solve this, now I'm going to make use of my definition. I'm going to make note of the fact that this is 10, a log base 10. And so my definition, y equals a to the x, is the same as x equals log base a of y. And so in this case, I've got the log base 10 of something equals 1. So that means that I get x plus 2 times x minus 1 is equal to 10 to the power 1. So this base to this value becomes my exponential part, and this just becomes the value on its own. But this is a quadratic, it's a simple quadratic. So this is x squared plus 2x minus x is plus x, plus 2 times negative 1 is minus 2, 10 to the 1 is equal to 10, x squared plus x, in this case minus 12 equals 0, and we end up with x minus 3, x plus 4 equals 0, which gives me two solutions, x equals 3 or x equals negative 4. Now, I say to check your solution, but before we check our solution, I'd like us to think about this a little bit as well, which is these are both variables that are in logarithms. So when I'm going to say recall that if I have y, actually I need to do this to the side because this is rough work, it definitely doesn't belong here. So recall that if I have y equals log of x, then this value, the argument that I put in here for my logarithm, has to be, oh, I realized I just made I realized the mistake I made on the previous page. I'll have to go back and take a look at that with you in just a moment. This value x has to be greater than 0. And that is because of the graph. The argument to a logarithm has to be positive. So this value has to be positive. So that means that x plus 2 must be greater than 0, which means that x must be greater than negative 2, and x minus 1 must be greater than 0, which means that x must be greater than 1. But x equals negative 4 is a fail because x equals negative 4 is actually less than both of these. So this one is inadmissible. And so therefore my solution is simply x equals 3. And so if x is equal to 3, we're going to check that solution. We do our check left side, which was log of x plus 2 plus log of x minus 1. Log of x plus 2 plus the log of x minus 1. That becomes the log of x plus 2, which is 5, plus the log of x minus 1, which is 2. And that becomes the log. Well, we could calculate this, but you know what? I think that's safer. Let's go ahead and calculate this. We put this into our calculator. We get the log of 5, which is equal to 0.69897 plus log of 2, 0.30103, and we add those together and we end up with approximately, not 10, we end up with 1, and our right side was equal to 1, so my left side is equal to my right side, and that works. Just to remind you where this is coming from, my right side was equal to 1. Now to go back, I'm sorry I made a mistake. On the previous page, I referred to x as the base of a log function, therefore x must be greater than 0. That's true. We've talked about that. That is true. However, I then went over here and I referred to the x value, the input to the log function, having to be positive. That was incorrect. Y equals log base a of x. While it is true that a must be greater than 0 and x must be greater than 0, this x was referring to this a value. So even there you see me getting tripped up over the kind of liberal use of variables that we do here. I used x for the base here. We solved for x, but I need to keep in mind that that's coming from this definition. Apologies for that. One of many that I have to make as I do these video lessons. Okay, so we're on to our assigned work. We're going to stretch this out into two. It's covering two sections from the book. So your work that we're going to want to take up at the beginning of the next class is this first section. And then in that class, you can keep working on the next section. So we're going to take 2 days on this. We're consolidating all of the skills we've done up until this point and putting them to practical use. So it does deserve a little bit of extra time.